consider that chlorine, on Earth, the average atomic mass of chlorine is 35.45, and that there are really only two isotopes of it. There's chlorine-35 and there's chlorine-37. Considering that, which isotope, chlorine-35 or chlorine-37, is more prevalent on Earth? And what percent prevalence does each of those isotopes have? Now, you can solve this using algebra, considering the equation that we saw in the last video. What you could do is say that the weighted average atomic mass is 35.45, and that, you know, is equal to the percent of each isotope times the mass of that isotope, all divided by 100%. And so you can plug in here, but you also would have two variables, chlorine-35% and percent chlorine-37. Having two variables, this problem is very difficult. However, what you can do is say that those variables relate to each other. You could say that combined, they would both be equal to 100%. And so you can assign chlorine-35 as being equal to 100% minus the percent chlorine-37, and then assign X as a symbol for chlorine %37, and then you can say then that chlorine-35 is equal to 100% minus X. And so you can plug in and have now only one variable, so you've got 100% minus X as your chlorine-35%, and you've got X as your chlorine-37%, and this should allow you to find the percentage of each isotope. Now, this is a kind of a long, drawn-out process involving algebra, and other problems kind of like this, they will not be solved in exactly this way. And so I'd like to introduce to you another way of solving a problem like this, where we're asking what percent of two different things do we have. And so I guess I'd like to introduce that there is a linear relationship between the average atomic mass and the percent of each isotope. So, for example, we could say that if we have 100% chlorine-37 and 0% chlorine-35, then our weighted average atomic mass would be 37. And if we had 0% chlorine-37 and 100% chlorine-35, then our weighted average atomic mass would be 35.00 atomic mass units. And we also know, using the fact that our equation that we were just working with involved only, it wasn't a quadratic or anything like that, it was just linear. We know that having 50% of chlorine-35 and 50% of chlorine-37 will give us an average atomic mass of precisely in between 35 and 37, 36.00. And so you can see that there is a line, there is a linear relationship between average atomic mass and the percent of chlorine-37. Now, considering that it is a linear relationship, I usually like to think about a number line, kind of restating what we were just saying, but without drawing out all the graphs. You'll enjoy using these number lines later. We can see that the weighted average atomic mass we actually find to be 35.45 AMU. And so our first question is, which is more prevalent, chlorine-35 or chlorine-37? Now, you know that if you have 35.00 atomic mass unit as your weighted, then you have 100% chlorine-35. And if you have chlorine-37 as your weighted average atomic mass, then you have 100% chlorine-37. Now, this mixed number, this is much closer to chlorine-35 than to 37. And so you should presume then that you have more chlorine-35 than chlorine-37. Just like you recall, when our weighted average atomic mass of carbon was 12.01 atomic mass units, you could presume that there was much more carbon-12 than carbon-13 around the Earth. You can do a similar thing with chlorine here. And so this allows you just to get a guesstimate about which isotope is more common, but this number line also allows you to do a very quick calculation about what percent of each isotope exactly do we have. And so you can consider this equation, which I kind of made up here, but actually tends to work for all the types of problems that we're discussing here. You want to take the greater pure number, subtract the mixed number, and then divide by the difference between the pure numbers, all multiplied by 100%. So this applies not just to isotopes, but to percent of one compound versus another within a mixture. And we'll see a lot of this in the rest of chapter 3. Now, all of this gives us the percent of the smaller pure number. Okay, so let's plug in what is the greater pure number. So what is the greater, atomic mass? Well, it's 37.00 atomic mass units. Our mixed number is our mixed, or our weighted average atomic mass, that is 35.45 atomic mass units. Now, the difference between those pure numbers. The difference between the pure numbers, so the mass of chlorine-37 is exactly 37.00 atomic mass units, and the mass of our chlorine-35 is 35.00 atomic mass units. And so, kind of simplifying this equation, we should see that we have 37 minus 35.45, that is 1.55, and 37 minus 35, that's 2.00. We can then calculate then that 1.55 over 2.0 times 100% is 77.5% is our smaller of the pure numbers. And so 77.5% of our element is chlorine-35. And then considering that we know that the percent chlorine will be 100% minus that, it will be equal to 22.5%. I just kind of view this on a number line a lot of the time without even writing out that entire equation. What I do is I say the difference between chlorine-35 and 37 is 2.00. The difference between our smaller and our mixed number is 0.45. Or I could say that the difference between our mixed number and our larger number is 1.55. Considering either of those, I can say that I have, say, 0.45 over 2.00 times 100%. I have 22.5% of one of the isotopes. Which isotope do I have 22.5% of? The one that this mixed number is closer to, or the one that this mixed number is further from? Well, it's the one that it's further from. And so we can look at this and we can say, oh, well, we must be 22.5% chlorine-37. Or you could say we have a difference here of 1.55, so divide by 2.00 times 100%, and we get 77.5%. 77.5% what? We've got more than 50% of something, and that more than 50%, that will be the one that's closer to the mixed number. So we're 77.5% chlorine 35. We'll be practicing problems like this very frequently.